So I guess I'm subscribed to my own channel. So I take a minute here for the warm up. We've been doing some tech talks in the morning. We talked a little bit about AI. As everybody knows, if you follow the channel, I've been working on a PhD in computer engineering, and my advisor retired. I was working in quantum computing, and I live off grid on solar. And because of some of the difficulties in the winter, the weather out here, I've been exploring micro personal reactors. And we're talking about something you put on a boat that's safe to be around. Several of my designs are basically batteries. It's basically a thermonuclear radio generator, an RTG, um, which has a very small amount of nuclear material in it and a thermocouple, and it just generates electricity that way. It's very, very low level. They're very small. These are, a football or slightly bigger, and the shielding on them is very small. A lot of people work on nuclear submarines. This is smaller than that. So, nuclear powered boats. The other one is a hybrid accelerator driven reactor. We use some base metals that have a particular isotope that's reactive when you hit it with a different radioactive source. So there are a neutron generator, whether that's going to be a small amount of tritium or something else that would be energized. You can turn this off and it stops being radioactive. It just stops being radioactive when you turn it off. Your glow in the dark watch is going to have more, right? It's going to have more radioactivity than this thing. So that's the idea behind a couple of the generators I'm working on. Um, and I say generators, reactors. These are reactors. They are a nuclear reaction, but the hybrid accelerator driven one gives me a lot of promise, um, especially when it comes to resource utilization. It's going to allow us to take things that are otherwise harmful for the environment that get thrown in landfills, and we'll be able to use those as our catalyst to create the reactors. So that'll allow us to recycle hazardous waste instead. And when they're done, there is almost no byproduct waste whatsoever. It's minuscule. These are very tiny. So as we move into AI and power generation, of course, I wanted to talk a little bit today before I head into work. I'm doing some work over the summer here to pay tuition. I'm self funded. My advisor retired. They had some health concerns. I have tremendous respect for my former advisor. They're one of the smartest people I've ever met in my life. And what they taught me physics I didn't know existed. And they talk about the iceberg, about what you know and what you don't know, and what you don't know, you don't know. Some of that stuff. And so this guy, I come in and it was just, he taught me things about physics I never even knew existed. I had some vague, distant conceptual ideas of this in my reading, but for them to just break it open, like to say, hey, here's some people you never heard of, some amazing scientists you didn't ever know were alive, and this is the work they did, and this is what they proved works, and this is how this quantum computer works. So I have tremendous respect for that person. So when we start talking about advanced computing platforms, not just quantum, because quantum it's such a buzzword, it's such a misnomer, and so is AI. I had a guy a while back, he worked on some blockchain. I guess he knew Satoshi, and had worked with him online on some projects, and they worked on some other blockchain product projects, and we had talked about some different technological advances, somewhat in healthcare and in life extension, how to improve longevity. And I haven't talked to that guy in years. It's been years now, but it's back in the day when Freenode was still up. And one of the things that we were talking about was blockchain is just programming. It's just code. That's all it is. It's a lot of programming. There's no magic secret anything to it. It's just a set of code. And I think the same thing is true of AI today. When you take a step back and you look at it, it's just code. It's a lot of statistics. It's a little bit of calculus. It's a lot of statistics. It's some matrix math. And when we start talking about Markov processes, we're really talking about intercept code. So I wrote some AI for games, and if you think about something like Space Invaders or Galaga or whatever, asteroids, and you have a thing moving, a ship moving, and you want to have a homing missile, okay? You want a homing bullet that goes to your enemy. Well, it's going to adjust based on where it is and try to hone in on where it is. That's chasing. It chases the enemy. It goes to where it is. It changes its direction of travel to try to line up with where it's going. That's chase code. And then evade is this thing's trying to not be where this thing's going. And then intercept code is I'm going to move my vector so that I'm going to be where the other thing is. And they all require increasing levels of information. Chase, evade, intercept. It's real basic video game code. Okay, chase, evade, intercept. And you think about that. The fox chases the rabbit and it tries to go towards the rabbit. And then the rabbit tries to evade. It tries to go where the fox is not going to be. But a lion intercepts and it moves to where the rabbit is going to be at. Chase, evade, intercept. And so it's just increasing amounts of information. I know where this is. I'm going there. I know that this is moving towards me and where I am. So I'm going to move away from where it will be. And intercept is going to be, I'm going to move where it's going to be. So I know how fast, not only where it is, but how fast it's going and in what direction. Okay. So increasing levels of information. And Markov processes are basically the same thing. It's a big matrix of the same thing in multidimensional space. And then you've got a lot of statistics, a lot of, if this is our probability of this, this is what we want to try for. So I'm just going to take something simple like an image generator. And it uses a generative adversarial network. This is how Midjourney and Deep Dream work. They look at millions and millions of pictures and they create a model and they assign a tag with it, a word, lion, dog, grass, tree, car, bicycle, whatever. And it has all of these images associated with it. And what it tries to do is randomly, statistically say, if I put a pixel here this color and one over here that color, then statistically I'm close to what those are. I'm very similar probability-wise. And that's a probabilistic model. And a ton of the AI works on this. Your LLMs, your big Chat and your Grok and Gru and your Anthro and all that stuff, those big LLMs are the same thing with words. You ever play Mad Libs? You pick a word, you pick a verb, it's next prediction. And if you've ever talked to a flim flam man, somebody who can sit there and sound smart, you can talk to them about things and they throw words at you and they say, oh, but I meant this or I mean that. Well, if you look at it this way, it really, and they bring it back around. They're good at steering a conversation. They're flim flam answer, they're con artists. That's what the AI is doing right now. It's using Mad Libs and then rejustifying in many, many cases. So what we do have is a thing called constraint-based programming that's used in optimization. Things like the simplex method, complex system analysis. It's not just gradient of least descent. That's, again, your statistical. What's our most likely next step to get to our least error? Okay, gradient descent. What's our next step to go to our least error so that we're the closest to it? And you really have to study a little bit of statistics, not just mode and mean and average, but you need to look at your deviations, your standard of deviations, your number of standard deviations, your variance, your analysis of variance, that kind of thing. And and that comes into play. But that's a lot of what they're doing. They're guessing. They're statistically guessing at the best answer. They're not really creating it. So part of this is the libraries that are used are not built around constraint-based logic. There are a lot of them are done in Python and C, which are great for, C is great for crunching numbers. That's what it was built for. It was built for computing, and you got to go back to the PDP-11 genes. The PDP-11 genes are strong in the x86 because that's what the x86 was, the big Intel processors. They were miniature PDP-11s. PDP-11 was a big old mainframe back in the Unix days, back in the early 70s. And the x86, the 8088 and 8086, and from it the 286, 386, 486 Pentium, right? All of those are in that same family, and they were stripped down PDP-11s. That's what they did. They could run something very similar to what a PDP-11 could do, cheaper and a little more optimized. They had few less of these special purpose registers because registers were the big thing then. And so they're really good at crunching numbers. They're great at it. But when you start to look at something like logic or constraints, you need a language like Prolog. And Prolog, it's kind of like Lisp. Lisp and Prolog, they're like two sides of the same coin-ish. I'm not trying to make a big assertion there. It's just an example, but Lisp is a list instruction set processor, and Prolog is a programming language for logic. And you can create a Prolog in Lisp, but you can create a Lisp in Prolog a lot easier. So you can create the Lisp language and implementation of a Lisp in Prolog. And Prolog is all about predicate logic. It's all about constraints. So a dog is, a cat is, yellow is. And we can define yellow. Yellow is a vibration of photons at a certain frequency and wavelength. We can say red is what, 450 to 492 nanometers or something. It's 400 and something nanometers is the wavelength on red. And anything that's not moving that fast is not red. Red is not subjective. There is an objective reality to what red is. We can subjectively say where the boundary is that this is kind of red or not, but we can clearly and absolutely identify what colors are. We can do that. We have entire sciences around different lab formulas and dye and ink formulas and light mixtures to define what a color is. And so it's not statistics, it's objective reality. And so that's kind of the difference there. We can say that looks like a dog or that is a dog, right? Those are two different things. Something can look like a dog and be the bark on a tree, and it looks like a dog, right? It's easy to make that, but it's not a dog. A dog is an animal. A dog is a living creature or once living creature. A dog has fur and forelegs. At birth, normally has four legs and a tail and ears and an elongated snout, and is a mammal. And we can define what a dog is very, very. So we say its chromosomes are. Okay, the chromosomes of a dog are this many long, and they have these genes. We can objectively define a dog by its chemical definition of its DNA. We can say that. Okay. And so Prolog is like that. You can objectively say what is or isn't something. The house is red. The house is blue. Billy lives here. Tommy goes to school at this university. And those are all things you can do. There's no subjectivity to it. So this is constraint-based programming. And this is where I say we get into optimization and things like the simplex method, which are all about finding an optimal form based on constraints. So you take your graph and you say something is less than this, where you're going to shade off everything above, if it's less than 5, okay, it's more than 4, right? So it's between 4 and 5. No, we've shaded off everything below 4 and above 5. We can say it's X plus whatever, and you get these different things. And then you just kind of go around and you find your optimal point. You go around counterclockwise on your graph, simplex method. But they're constraint-based logic. It's a constraint-based form of optimization. And I think that's one of the things we're going to look for more and more, not just in symbolic math and symbolic programming languages, not just in symbolic representation and saying we have an X, we have pi, we have a summation, there's a numerator, there's a denominator, not just in that kind of symbolic math that can be solved. If you have a calculator with a CAS system, computer algebraic solver, computer algebraic system, some of the really new Texas Instruments and Casio calculators have them. You're going to get back to that point where you can have that. But we also need this constraint of logic. We're going to need the ability to do this. And it's going to take new hardware. It's going to take a new way of programming and using our memory and using our computational resources to create and implement these constraint-based resources. Absolutely important. I mentioned Lisp, and Lisp is all about, it's a parenthesis language. It's all about nested lists, nested sets. And that really goes back to the PDP-11 genes of the cons and the car registers that get the catter and cons registers, and how they move things from the left side to the right side and compared them. And so Lisp was definitely implemented heavily on there. And if you want to compare lists, is this similar to this? Is this the same as this? Are these in the same set? Your PDP-11 genes, your x86, your Lisp-based languages, Python, they're all going to be fine at that. But as we move into more logic-based programming with languages like Prolog and similar logic languages, we're going to need some new paradigms. And I do believe that in-memory and near-memory computing is going to be the one there. So right now you have your CPU, and you have RAM, and you have a hard drive. And on your CPU, you have a little bit of cache RAM, so it doesn't have to go as far. Your most expensive thing, whether it's time, computational resources, electricity wise, is to go get something and move it to RAM and to take it from RAM to the cache. It takes so long. So if we take mini processors, not a whole giant processor, but a little mini processor, and we put it in the RAM every so often, we can distribute our algorithms out to this. So you talk about multi-core. I'm talking about having thousands of cores that are really little. So how do I put this? Instead of a big semi engine that moves the semi truck, okay, or even a car like a sports car that goes really fast, okay, big semi truck, Ferrari, they both have engines, so many horsepower, the transmissions are different. One goes really fast and the other one pulls a lot away. They both burn a lot of fuel. I'm saying having, and this is going to sound silly, it's a bad analogy here, having a whole bunch of lawnmowers or weed eater engines that are doing a little bit in tandem, in unison. Okay. And that's distributed processing. And it doesn't seem to make sense in a car. It would be odd to have a car, but here, let's put it this way. What if you had in the electric cars, instead of having one central motor in the car, a train, right? It's got that one big central engine. What if we have a motor in each hub, in each wheel? It's distributed. Okay, that's maybe a better example. So a train has a big diesel engine, and the diesel engine makes electricity to run a big electric motor to pull the big train. And as some of the electric semis are doing the same thing, they've got a big electric motor and a generator to generate that to pull it. And one, they've got a central location and it goes to a transmission that goes to the drive wheels through a differential. I'm saying more like having one motor in each wheel, right? Hub-based motors. And they do that in a lot of electric cars. And so that's kind of the distributed processing. We're going to spread out the load, and there's advantages to both. But I think in computing, you're going to have a little miniature processor, right? It's going to just be like a small RISC-based processor. It's not even going to be like RISC-V. It's going to be even more simplified than that. And you're going to have dozens of them. You're going to have like dozens of these micro cores, and they're going to be in every chip of RAM on that stick, or there's going to be 10 of them in each piece of RAM. And you're going to send out your instructions, compare these numbers, add these numbers to this other number, subtract this number, multiply this, perform logical operation, ands, ors, xors, things like that to these numbers that are in memory, and do them repeatedly. Because that's a lot of what we have is go and fetch, bring it back, do an operation, put it back in memory. Go and fetch the next one, bring it to the computer, do the operation, put it back in memory. There's a lot of fetch and go. And that's kind of just how things are because of the nature of computers and the way they were built. So in memory and near memory computing is another one. Three-dimensional structures. So right now we have multiple layers, but mostly on the chip, you've just got a two-dimensional grid. I think as we start to see branching that can go up and down to different layers, I think that's going to be a big one there. Three-dimensional computing. I'm really excited as somebody who worked in quantum. I'm really excited about single molecule computing. I think that's going to be a step forward to biological computing. And when we get to biological computing or molecular computing, the difference there is really subtle. Biology is a molecular system. Your brain is a biological computer. It's a molecular computer. It uses molecules in your brain, right? In your brain cells. Okay. So I think that we're going to move more that direction. So just some things to think about there as we move forward in AI. This is going to reduce our electricity cost. It's going to make things more efficient. It's going to bring us to better constraint-based programming, better logical-based programming, better programming models that aren't just statistical. There's so much right now that's just good guessing. And I would like to see us move past good guessing and into formal logic. So we need to have programming models that don't just sound good. They're not just flim-flamming. They're not just conning and sounding like they're smart. They're giving you what seems like it should statistically be a good answer, the best thing to say. We want to have something that logically, through a clear set of objective constraints, objective facts, brings us to our answer. And that's going to be computers that can do philosophy, that can do logic. And it seems funny to say computers can do logic, but I mean that it can actually perform predicate logic. This is A. This cannot be that because it's not this. So I've got to get into work here. We're getting up to that time. It's been about 20 minutes chat, and I just wanted to take a moment today to talk a little bit about AI technology and computing technology and where we're going with it. Constraint-based programming, logic-based programming, in-memory and near-memory computing, and some more advanced computing structures. We're going to get to, instead of having a capacitor and a resistor that are, a wire and this and that, it's going to be one molecule. It's going to be a little piece of cadmium. It's going to be a little piece of calcium. It's going to be a little piece of whatever, strontium, whatever, beryllium. It's going to be these things, and they're going to create our computing structures at the nano level, at the cellular level, and that's where we're moving in it. So, and that's going to allow us to do some real distributed computing with massive multi-core computer, not just 64 cores or 128 cores of a big Xeon or a big Pentium 7 i9. It's going to be 1,000 cores, but they're going to be like little beady computers. They're going to be like, right? So, hi to chat. It's good to meet you. I've got Ismay. I've got to get out of here. I've got to get into work. I've got to pay tuition, so I've got to work because I don't have an advisor right now. So I will see you all another day. Okay? Be safe, chat. I got to go to work so I can pay for the PhD so I can keep working on this cool stuff. I'll see you, YouTube. Thanks for dropping in. This weekend, I may do some nature walks from the house. Izume, Clamor, it's good to see you in chat. 3 Arcanics, thank you for the vote of support, and I will see you all next time on the Tech Talks at Wayfarer Technologies. I'm Storyteller.